Tonight's a really special night where we get to talk about rolling of steel tonight, and the part of the lecture series. This is the sixth and final, this is the fifth of six lectures that we have for this year, where we talk about the people, process, and products of the Lukens Steel Company and its long history, and continues to roll steel today under ArcelorMittal. But we really are as well want to thank the Lukens Veterans Guild for pulling this together. Sharon Handrich and John Wickman, who's the president, for doing this. I believe it's the 70th anniversary of the Lukens Veterans Guild, so we're happy to have them participate in our lectures tonight. Again, just everybody enjoy tonight our lectures, one of many programs. We also have a concert coming up, a Victorian dinner, and in the second weekend in December, we're having a holiday open house where the houses will be decorated, and we're doing a food drive. But tonight, is really about rolling, and we're very excited. But at this point in time, I'll just introduce John Wickman, the president of the Lukens Veterans Guild.
Thanks, John. Thank you, Scott. Good evening for those of you who don't know me, and most of us know each other, worked together for many years. I'm John Wickman. I'm the, I think, 66th president of the Lukens Veterans Guild, which was founded in 1937 to honor people who worked for the Lukens Steel Company for 20 years and more. And we currently have over 400 members, retired now, of course, and spread all over the country. Many of them are around this area. And we hold, have an annual dinner, hold meetings, and you're all invited to join if you haven't already, and you'll be most welcome at the meetings. Tonight, we're going to talk about rolling, as Scott said. The Veterans Guild is very pleased to join with the Greystone Society to sponsor this event. Lukens is a, if you ask people what is Lukens Steel Company, they say it's a plate mill. Well, rolling is what produces the plate. There are things that happen before it, very important things, melting, very important sophisticated things. Things that happen to the plate after it's rolled, or reduced to the thickness that the customer wants. Heat treating, finishing, descaling. But you have to produce the plate. That's the primary product that's going to be shipped to the customer. And we have with us this evening two people who have much experience and who are really leaders, and Mike is still working at ArcelorMittal, is a leader in the ArcelorMittal organization. Lukens people who produced, and we're all very proud to say, always proud to say, a wonderful quality product. And before I turn it over to them, let me just give you a little bit of background. For the two speakers, Dave Rodriquez over here came to Lukens Steel from Scott Paper Company in October 1957. He worked first in the industrial engineering department, and then he went to the rolling department, where he had a variety of positions, including supervisor of the 120-inch mill, supervisor of the 140-inch mill, and then he became superintendent of rolling following the retirement of Jim Taylor. And Dave can tell you he retired from Lukens in 1984, and I think he's enjoying it, and I hope he is. Mike Kessler began his career at Lukens in 1976 as a technical assistant. He started working at the rolling complex in Coatesville, and then in 1988 went to the 110-inch mill in Conshohocken. He is currently the division manager of manufacturing for the 110-inch mill under ArcelorMittal. And I don't know which one of you gentlemen wants to begin the discussion. Maybe Dave. I think he's has the right of being senior person here. So I'll turn it over to you, Dave.
Thank you. Thank you very much. Appreciate that. I guess I should open it by saying that this guy here I hired right out of what Fort Campbell, Kentucky, the 101st Airborne Division out of West Point, and then retired from the service after his 5-year military obligation. We had a number of military people come through our organization, and Mike was one of them, and Mike stayed. But I go back, as Don said, to 1957, when I came after 4 years with Scott Paper Company following military service and then college, and then started out in the industrial engineering department under Bill Taylor. And then subsequently, as the openings arose in the manufacturing division, I ended up in the rolling mill as a technical assistant to the superintendent at that time was Jim Quarry, who has followed Lou Bunning, who was way back, goes back to the Bunning clan in Coatesville and Lukens. And starting out pretty much in the heating department where we started the process for rolling. You had to get the steel hot to roll. You had to have the proper metallurgical temperatures and the observers reporting of the temperatures to the heaters, and then subsequently putting the steel on the mill for rolling. And all of that time, it was more or less a training phase for what would take place further on as foreman of heating, assistant to the superintendent, and then supervisor of the 120-inch mill and supervisor of the 140, 206-inch mill. But to go back, the rolling department at that time was made up of the 120-inch mill, which was installed during the war as a wartime mill, and then the shear line followed it, and then the 112-inch mill in front of the 120-inch mill. The 206-inch mill, of course, was preceded back in 1918 and then electrified in 1947. So there's quite a history of our equipment and the rolling facilities at Lukens Steel Company that cover a lot of years and a lot of history and a lot of people who have gone through the rolling mill operation. But my career has pretty much been all through that area, has been in the rolling area, starting out again, as I said, in heating. Then we developed what was known as trying to get away from the 3-high, 2-high situation where we had older electric-driven mills, but older mills that did not have the capability and the strength to do what we were trying to do with heavy gauge plate. So the episode, as we go through the history of the rolling mill, we developed the feeling of the theory of the 140-inch mill. And this was pretty much an operation where we were able to take the vertical mill and squeeze the ingots rolling at the time and save the yield. Yield was a big factor when you're rolling. The rolling mill process flattened out, and you ended up with an awful lot of side scrap, end scrap, which was wasted in the following of the cutting of the operation after following rolling. So the development of the 140-inch mill in the early 60s and late 60s, when it was finally installed, was a tremendous move for rolling mill in the 142.6 mill complex. It replaced the old 143 high mill, which had no edger capacity, and it was the forerunner, of course, for strand casting. All of these things are evolved over a period of years, and then we eventually ended up with 2 strand casting machines down at the electric furnace, which then negated the edging process on the 140-inch mill. Through all of this operations and all of these transitions that we were going through, yield was the number one consideration. You take 10 tons of steel and you get 9 saleable tons of steel is what you wanted. It was all based on yield and what we could save in side scrap and end scrap. That became the guiding light for profitability of where we were headed, of getting the most out of a 10-ton ingot, 50-ton ingot, whatever size we were rolling, as to how we could get improved yield. And instead of putting a 50-ton ingot in, we put a 45-ton ingot in, get the same plate. And this is where the saving was involved, and this is how you generated monies for investment, for future investment in your equipment. From there, we evolved into, let's start talking automation of the rolling process. All the time that I was in the rolling mills, it was all pedals. start and stop, reverse, forward and reverse, in the lever, put the screws down, take another pass. The screws were kept at the opening of the rolls. Then you take a screw down and reverse the mill, put the piece through, back and forth. All of this time, automation was coming into play as to how we could go and say, let's put a computer and then go with what we have. And we take the operation, take the feet from the man, put them back underneath his tail, put his hands here, and then let's go. Then we'd roll the piece. That took a period of probably 12 to 14 years, I'd say, of my time in developing and where we were headed for automation. That's when Mike came on board. As we went through the process, the older guys faded off the picture and retired, and then the young Turks came in and carried it through. Now, all the time we were doing this in terms of people. Jim Quarry took Lou Bunning's place, then Jim Taylor, then Rodriguez, and then Mike Kessler came on board. Bill Jasinski was in the 120-inch mill. I think Serena is still, Bill passed away unfortunately, but Serena is still up at the Coatesville facility up here. She is still around. We've had a number of people from Hershey's Mill, where my wife and I reside, Marge and I reside in Hershey's Mill, and she is still surviving over here in the Coatesville at the facility. And Harold Swore, Bob McMichael, Ed Fogelman, Newt Thompson, all of these people came through the process and the management of the manufacturing division of Lukens, which rolling, melting, and rolling and finishing and shipping were the primary factors.
Right,
After that, the Young Turks took over.
Who was principally responsible for the building, the justification for the new 140-inch mill?
That was primarily Bob McMichael. His idea was, and again, the guiding light was yield. The longer the plate you rolled, you only had one end scrap. This end scrap and that end scrap. Then you divided the plate. The old way, you'd roll 3 plates and have that end scrap. The second development was the side scrap, where you'd take the plate and roll it out on the mill, and you'd have 8 inches of side scrap on each side that had to be trimmed off. In the meantime, all you're doing is having more metal and more waste from end scrap and side scrap. The idea, the concept of the 140-inch mill was to bring the vertical mill in behind the rolling mill, and as you reduce the ingot, you also squeeze the sides. So we ended up with a slabbing operation, which gave us a slab with solid sides, no overroll, no indentation for overroll, and you get a slab that was sent out to the steel yard and then cropped into slabs, subsequently sent back in for rolling to plate. That produced the forerunner of the strand caster, later on developed for down at the in the melt shop, to put the steel right through a caster and give you the slab, eliminating the whole rolling operation of slabbing. Then you turned your mill into a plate rolling facility, slab the plate, ingot the plate, slab the plate. So you got away from slabbing operation totally. In all the processes, all the yield studies, we took yield studies day and night, month after month, of how to reduce the 8 inches on this side, the 8 inches on that side, down to 2 inches. How to reduce 3 feet from this end, 3 feet from this end, down to 1 foot. That became the yield, and that became the guiding principle of the rolling mill department all through the 60s and 70s and even right through the 80s.
And when did Plan F come? 62, right? Plan F was 62-ish?
Yeah, 62. Then what we developed was the S&R mill, the 140-inch mill, which was slabbing and roughing. The S&R became more a plate rolling facility than a slabbing operation. So the plate rolling extended north, and the first thing we did was open up the end of the building and roll them plates out on the north end on temporary tables. And then an engineering study developed, starting with Plan A, B, C, D, E, and finally Plan F.
That's new to me, but that's
how it got down.
I didn't know all that.
Vince Ponja and Mal Antrim, I guess, was chief engineer at the time, manager of engineering at the time. Bill Binzer, Vince Ponja, all of those people in engineering at that time. We went through a phase of Plan A. We put the print out and everything, didn't like that one. We go back and redo it. Plan B, Plan C. It finally developed into Plan F, was the one that was adopted, passed by the board of directors, and then we capitalized, spent the capital and
how much
went
did that
out.
cost? Do you remember?
It seems like it was
Skip ought to know
13 or 14 million dollars.
Oh, my gosh.
It was nothing,
Hey, Ron, one of the things I think that may be very important in this discussion of the rolling is your time management for heat, because it's so important to try to keep the heat up to a pliable temperature. So you're racing not only against the yield, but you're also racing against the heat, so that you can continue to roll the plate before it got to the point that it would crack and have to.
We used a lot of residual heat also in the soaking pits. We took the ingots from the melt shop and brought them up by railroad car and highballed them right into the mill and got them into the soaking pits hot, where you'd pick up the residual heat. It's just pretty much like you take your coffee cup and put hot water in it in the morning. You put the coffee in there, it'll stay warm longer. But we used residual heat wherever we could. And the soaking pits were a very expensive proposition. That was natural gas, all natural gas. And natural gas was pretty expensive at the time. And then we had to, when shortage of natural gas came, then we had to switch over to oil and heat oil. And that happened most of the time in the winter when we'd have a real cold spell.
And oil won't flow.
Then we'd switch over to oil, and that was unbelievable. And that was another very expensive. The big, I guess one of the highlights of the mill was the flood. I can't remember the year the flood hit, but we were totally wiped out.
79.
What was it?
79.
79. We had that sucker run or whatever it was called, went over the banks and just wiped everything out from Strode Avenue all the way down. All of our soaking pits there was just a cloud of steam in Coatesville. I mean, it was unbelievable, the amount of steam that was.
I remember one story about the flood. I'll tell a couple stories. One of them was that happened on a Saturday morning, and I was at home, and I came into work as soon as it happened. And one of the guys said to me, he said, that ingot, and we had rolled an ingot that was about as big as the chair's square, and it was sitting on the ground. And when the water came up out of Sucker Run, it came up and got under that ingot. And of course, when it got under the ingot, the water boiled. It lifted the ingot, the steam pressure lifted the ingot up off the ground, and then the water that was flowing along the side of it moved it, and it would set back down. And then the ingot would pick up in the air again, or up on top of the water, and it would move another foot or two and set back down. And that ingot had walked like 20 feet that morning from the waters coming through. I came in to get my shoes on in the mill office, and of course it was on the Sucker Run side. And I remember I went in the office, I put my foot, of course our office had been underwater, but my boots were there, and I had to put them on to go out in the mill. And so I put my foot down, and there was a crawdad in my shoe. And
that was a very expensive situation. Yeah. We lost weeks of production. I can't remember how long the 140-inch mill. We had to take every motor, table roll motor, all of the big motors, and then
6 weeks.
take them out and send them down to Elmwood Avenue. General Electric had a drying shed, I guess, or whatever it was, a facility for drying out motors. And it was one after another. We had General Electric trucks and Lukens trucks just back and forth every hour on the hour, taking their motors out, bringing them back, reinstalling them. When we finally got rid of the water was
Who was the big, tall engineering guy at that point in time? I remember that morning I took him over onto the east side, and we went down the steps into the motor room. He said, he came and got me and said, I want you to go down into the motor room. Take me down in the motor room. And I looked at him like, you sure you want to do this? And so we went in the side stairs, and we went down about 6 steps, and we stopped, and I shined my light into the water.
Yeah.
Well, at that point, we were still a story and a half up in the air in the basement.
Oh,
we were
no.
still 15 or 20 feet from the basement, and of course, all of our motors. And he grabbed his chest. I thought he was going to go down. I thought he was done right there.
No, that was quite an experience, and a very expensive experience for our company. I know that. We were socked out for.
We were down 6 weeks at the 140, but the next week we started rolling out of the 206-inch mill and using the debuilding soaking pits.
Yeah, because
We saved the water
the
from that
old
side.
206-inch mill was above ground. When the new 140-inch mill, that was all developed underneath. But the 206-inch mill, the model out here that you see, that was all above ground. Once we got the water down at that level, we got that mill going.
Next
And the
week,
120-inch mill wasn't affected.
we went back to rolling side scrap like the old days.
Yeah.
And your mill stands are very much like an iceberg.
Oh.
10% above the ground, the rest
Right.
is
Oh.
underneath.
Right.
All right, Mike, you can handle it from there.
Okay. I'll go back while we're sitting here talking a little bit about some stories about the 206-inch mill and some of the products we made down there. And I remember rolling clad plates, big clad plates for Avondale Clad, big 4-plies and 2-plies. I remember selling tickets to rolling the titanium plates for the deep diving sub, the Alvin. They were rolled on the 206-inch mill. I remember that the morning after we got Rod pretty good, I was in charge of rolling, and another guy named Kamen was in charge of finishing and shipping. And we rolled these big, the Alvin's actually made of 2 hemispheres welded together, and they're titanium plates 3.5 inches thick. And they were given to us as titanium pancakes, if you will. And we had to roll them in one direction and spin them. You know, like you wanted to make cookie dough, but it had to be round. And so we would roll in one direction and spin, and roll in another direction and spin. And we practiced. And Rod and I, he made me practice. And we practiced on carbon until we got this thing right, till we could do it. But anyway, we rolled them, and Rod was my boss at the time, and he was all over us. I mean, every detail had to be just right. And we finally got them rolled one day, and we sold tickets. There must have been 150 people around that mill stand, the 206. From the Navy, and RMI was there, or time at whichever one it was. But anyway, we got it rolled, and we put the first pancake made. It was about 150 inches in diameter, this round piece. We put it up on pots. And I told Kamen, I said, we got to work something out for Rod. And so they laid the circle out that they were going to cut. And of course, we were months away from cutting this thing. And Rod came down through the mill, and they lit the torch as if they were going to cut it. And Rod came, what are you doing? And they said, well, Joe Lee told me to cut this as quick as I could. You turn that torch off. And he took 10-foot steps down through the mill till he got to Joe Lee's office at the south end. And he stood on top of Joe Lee's desk and yelled for 15 minutes. And finally Joe looked up at him and said, Rod, can't you take a joke? You remember that?
There's a lot of stories around the time. And they bring back so many memories. I looked out here at this 206-inch mill model, and there's there's a guy there throwing bags, there's a guy there throwing salt, you know, you can still, you know, you can almost smell it, the boom, and hear the bang and whatnot. But that table, right there where the guy is standing, had all the charge papers, and as you roll a piece, they nicked it this way, that this was the piece that was in the mill. Once it was finished, then you went out, and the next piece would come down. And it was called the gauger's table. It was actually, you know, a forerunner. All of this stuff is computerized now. This was all manual, everything. But we had an old roller. His name was Art Moore. And Art Moore would go around that table because it ended up a lunch table. And everybody put their, well, the crew, the mill crew, the guys that were throwing the salt in the bags would put their lunch out there. Well, Art Moore, for some reason, and I don't know what his background was, but he never brought a lunch. He ate everybody's leftovers. And sometimes they weren't leftovers. I left a sandwich there. I wasn't finished with it. But Art, you know, boom, it was gone. Well, in the process of rolling, after you get the piece in the mill and cross it off, you had to identify it. The heavy gauge plates you stamped with a hammer with metal stamps. Locked in, you stamped them. Light gauge plates, you had a metal thing with a holder, and it had hot chalk, what they called hot chalk. And you'd write in the charge and position. Last three digits of the charge and the position. How about that for memory?
Yeah, good.
And then you'd get that, and then the plate would go down through the leveling rolls and then into the finishing end of the 206-inch mill, or north, whichever. And down there, then they would take the plates off the run and stack them by the identification numbers. So the people later on in the finishing end of the business knew what plate they were working with. Hot chalk was the thing we used. Well, the guys on this particular shift figured, this guy has eaten our lunch for 6 months. We're tired of it. So they made a sandwich of bread and hot chalk that just came off the mill, and it was running. And I don't know what made up hot chalk. It certainly wasn't cream cheese. And they made this sandwich, they put it out there, and then they ate all around it. And Art finally got it and ate it. He took a bite out of it anyway. He almost choked to death on it. But people's stories, I can remember Hyman Rickover, ring a bell, the first guy with the nuclear submarines. Mm-hmm. And we had a sub go down up off New England somewhere. And Hyman Rickover came into our shop and said about the ultrasonic testing of armor plate for the Navy. And we used to do armor plate testing in so many feet centers all across the plate. And he said that from now on, all armor plate for the Navy, 6-inch centers. Ultrasonic 6-inch centers. All the way around the plate. But he was quite a guy. He had quite a career in the Navy, and actually he's the father of our nuclear submarine program at the time. Go ahead, Mike.
All right. Well, like I said, I started in '76, so I came in at the end. The 140-inch mill was the main mill, the one at the north end. Plan F was installed, which was put in 1962 or 63. The 206-inch mill was only used 2 days a week, typically Wednesday and Saturday. We would run daylight and 4 to 12 on those 2 days on the 206-inch mill. So we had a mill crew that was qualified on both mill stands. So it was quite a process of moving people from one mill to another mill and having the soaking pits loaded and all that, and dealing with rod, and it was like working in a goldfish bowl, because you had all these old people at that point in time who knew everything and you didn't know anything, and you were trying to orchestrate this whole deal and get it to work, And so you'd try to do something new, or oh, you can't do that, or if you did something and it didn't work out right, or it did work right, it worked. It was always an adventure with all the people around that knew so much about how we got here, and you're still trying to learn. Talking specifically about the mills at that point in time, the 120-inch mill, although I was a superintendent over there for a while, I don't know exactly the history of that mill coming out of the war, but I remember that there was a board where you could set up with cards, we're talking about automation, and have the reduction schedule of how the mills the rolls get closer together, and so therefore the plate got smaller. And did that come with the mill, Rod, originally?
Yeah, that came with the mill originally. When Lou Bunning went to Japan right after the war, when the Japanese were first starting to modernize or to rebuild, they weren't modernizing, they were rebuilding from the war. And he went to Iwata Steel, was the company the one that we modeled the 120-inch mill from.
Well, the 120 then had this circuit board or a way of having cards and some amount of, if you were making this plate, then this is how you made it, and it was all kind of automated. The 140 was kind of designed around that, but never got there totally, and so it was pretty much a manual mill. And I remember I always liked to go watch the mills run, and finally one day a screwman who was operating the mill said to me, he said, "You've been standing behind me for 5 years." He said, "Sit down." And so I sat down in the 140, and he said, "Go ahead." And so Harold Bledsoe was his name, and over the next few hours I rolled some plates on the 140-inch mill. And so then I made it kind of a practice when we were rolling something easy once or twice a month. I'd go to the mill stand when Harold was up there and coerce him into letting me get in and make plates. And so one day we had a pit of stainless ingots that some metallurgists had decided they were going to heat 24 in one soaking pit and Steinman. And so we had put 2 layers of literally ingots stacked in this soaking pit. And they were never, ever going to be hot enough to roll. And so I said to, the bottom part was never going to get hot. I said to Bledsoe, I said, "Let's roll the top layer of this thing." And I said, "Let me make them." And so I got in, and I'm making the top layer of 12. And I got done, and I stepped up out of the 140 to leave, and there was Ed Fogelman standing behind me watching me. He'd been in there for about 20 minutes watching me. He said, "How often do you get in there, Sonny?" And of course the union was okay with it because I wasn't trying to take anybody's job. I was just learning about the mill and enjoyed rolling plates. And so that was my little story about running the 140. I never had the bravery to try to run the 206-inch mill. I remember making down to 206-inch mill, we would make the deck plates for the carrier that's over here. And they were 3 3/4 or 4 1/4 inches thick, 190 inches wide, and about 500 to 600 inches long. They were a huge plate. They came from 120,000 pound ingot, and it took about 30 minutes to make a plate. And so we would take a big ingot out of the soaking pit and bring it right from the soaking pit to the 206-inch mill, and we would start rolling. And 25 to 30 minutes later, you would finish one. And there was a roller, his name was John Gill, lived here in Coatesville. He's passed on now. But John was probably the best 206-inch mill screwman that I had ever seen. And he was making one day, and it was cold. And of course, once you get it to a certain size, there's no going back. You can't put it back in the soaking pit, it's too big. And so the motor room guy who's running the motors calls John up and says, "It's starting to pop and crack over here. Things are getting hot, things are starting to arc." John says, "You leave that motor room, you shut me down." He said, "That'll be the last day you work." And he just kept right on going. Back then, you might draft 2 or 3 1/100ths of an inch per pass. And like I say, it would take you 30 minutes to finish that plate. And they were huge plates.
That's what you call worrying them down to gauge.
That was worrying them down to gauge. Those are HY80. Yes, Skip. Yes.
I have a question. What years were you rolling titanium?
Well, we are still rolling titanium. I'll turn it over to Chris, and you're still rolling titanium.
Yeah, we do.
Well, when did you start it?
I'd have to ask Rod that. When did you start rolling titanium rounds?
Oh, boy.
That'd be when the 140 came, right?
Yeah.
As the slabbing mill did you have the?
We still had the edging mill. We had,
Did you?
it was probably in the early 70s. Could have been late.
It was there when I got there in '76. So let's say early '70s.
Okay, I think I can confirm part of that. Jim Taylor, I had asked about Jim Taylor.
Right.
We hadn't rolled any titanium, if my memory serves me right. So what we did, the big 206 mill, you don't want to break it up.
Right.
Don't how fat the contract is. So we strain gauge with research and engineering. We strain gauge the breaker blocks, a screw down with a 206. I took it up to Lukens took it up to Lehigh and had it certified. The force, in other words, as you squeeze down on it, then it would print it out.
Mm-hmm.
So we brought that rig home, put it in the 206 mil, and for a month we had recordings of everything that was rolled, how much the separating forces were. So then comes to titanium. Jim Taylor asked me if I'd go with him on this, and we went in the mill, run everybody out of the mill. This is at night when we rolled titanium. And I would watch it, and if it didn't exceed what had been rolled before as far as the separating force, went through slick as a whistle. And that was because they had no way of knowing, but we had, well, for a month or two you roll everything that you do normally roll. So it stayed within that range.
Mm-hmm.
And so we said, phew.
Hey, Mike,
Yes.
you might want to mention the characteristics of steel in terms of carbon and alloy versus, say, stainless and titanium.
Right.
Which,
Okay.
from a color point of view.
Well, I guess carbon steel is and I'll give you an example of, let's say, a piece of steel that's Halloween orange, very similar to what you'd see out here in the model. Carbon steel, if I gave you a hammer, you could hit it, you could make a dent in it, you could leave an impression in it at 1600 degrees. Stainless steel, you would have to really wallop at it hard to get any kind of dent into it. Commercially pure titanium is actually softer than carbon steel, and the alloyed titanium, 6-4 titanium, is somewhat harder than the stainless. Chris can attest to that. Then you get to the hinges of hell and the gates of hell. And the hinges of hell, well, actually the gates of hell are made from an alloy that's called Hastelloy X or 625, that material is used in jet engines. And at 1600 degrees, if you hit it with a hammer, it'll ring like a bell, because it has to have the strength of cold carbon steel, because it operates in a jet engine at 1600 degrees, as you know. B2, we've never rolled on any of the mills here. I don't know of any real plate mills that have rolled any B2. That's what the hinges of hell are made out of. And it is the worst of all the materials. It's a very high moly grade, so it's difficult to roll. And we've rolled all of those grades except the B2 on the 140. And we always had, we built a little furnace for some of the, we called it the pizza box. And we would break the piece down to like 5/16 of an inch. And I always had a standing offer to any screwman that could make a piece of this 625 3/16 of an inch thick. And we would heat it up to 2100 degrees, bring it out, run the mill flat together, and pedal back and forth as hard as we could pedal. And we never got close to 3/16. And it was a standing thing for the screwman's wife and himself to go to dinner, but we never got there. So we've rolled some pretty rough stuff. A lot of people won't even attempt some of the stuff we've done on the 140, which was designed as a high lift slabbing mill, not necessarily as a plate mill. While Rod's thinking, I'll go on a little bit. So that was 1976. We just kind of honed in on the operation, and I'll go back a little bit to the yield comments. We at one point we did get the strand cast material, got away from more ingots, got into more strand cast material, which was higher yield. Called the Japanese in at one point. They were the know-alls, and the guy came in and he told me, we showed him some plates, and we had this much in scrap left on the plates. And he looked at me and he says, "You don't need me yet." He said, "When you get to this in scrap, call me." So we have made progress over the years down to that point. That brings up another, going backwards a little bit to the stainless discussion. The 140-inch mill probably rolls 60 to 70% of the stainless plate made in this country is rolled here on the 140-inch mill. And the Japanese and Europeans have come over, and I have to tell the story about the Japanese guys. We would roll relatively small pieces of stainless, and wasn't uncommon for the stainless to turn up. And so maybe it's 4 or 5 inches thick, and it would come out of the mill, and it would roll up like a cradle. It might be this high on both ends. Well, now you've got a little problem. And so I was in the pulpit one day with 2 Japanese guys, and this plate came through the mill. Bledsoe was in the chair, Harold Bledsoe, and the plate turned up and stopped. And then one Japanese guy hits the other one, and he says, "Oh," which means these guys are really in trouble now, right? Bledsoe, what he did is he rocked the piece sideways and kicked the corner down and timed the rock, okay? Put a big screw on the plate to put a lot of pressure onto the plate, which is the way you have to, we called it breaking the back or laying it down. And he rocked the plate up to the mill, timed the rock so that one corner went in. At the same time that went down, he put the bottom descaling sprays, which is a unique feature of the 140-inch mill, to just be able to put high pressure water on the bottom of the plate. And so the plate came through the mill, high pressure water on the bottom, big screw, laid down flat as a flitter. And the Japanese guy went, "Oh!" Which is all you need to know about that.
Hey, Mike,
Yes.
while you're thinking about that, staying with the descaling, I think it's kind of interesting when you talked about the salt bags and the salt. I don't think maybe the people here understand that the reason for the salt bag and the bags was as a descaling.
Right. When you heat a plate up, it rusts faster, and so you have an oxide surface on it, and you have to get that off. And you use high pressure water. Unfortunately at this mill, still both mill stands, we suffer from a low pressure water, which is about probably 16 or 1700 psi. You want to be in the 3,000 to 4,000 psi range. To accommodate that down to 206-inch mill, I think there's like 1,400 psi down there. We would throw salt in bags, and that's what you see the gentleman out here in the model doing. The guys used to throw salt on the plate, and then they would throw bags on, and they'd try to get the explosion to occur at the right time so they could shoot the bags up through a window. You remember that? That was always the prize if you got one through the window.
They also like to do it when you had visitors. You take visitors down through the mill, and obviously you would want to show them this boom and bang and bags flying bit. But unfortunately, we had some guys there, instead of 3 shovels full, they'd put 8 shovels full, and the boom would knock all of the dust off the rafters. And they'd have our guests walking around. They'd walk down through the south end of the mill still trying to clean their jackets.
Well, you'd always try to warn them of that, if you had somebody coming through. And I remember one day I had a guy from GE, and he had a $500 suit on. And I forgot to warn him, and we were right up near the mill, and it was wet because there's always water and stuff there. And sure enough, we had our back to the place, and the guys had thrown the extra salt, and it exploded, and he broke to run and fell. Right into grease. I felt really bad about that.
Mike, I'd like to follow up just a little bit on the scaling. You were there at the mill opened up in Conshohocken,
Yes.
And remember
Well, I wasn't there when it opened, but
with the scaler, the guys they couldn't get the scaler to work properly. They were really upset about it.
Right.
And it turned out Leo realized that they had it on backwards.
Oh, okay.
And when they got it set, right, Rod?
Yeah.
And when they got the thing finally set up, it just, excuse the expression, had the smoothness of a baby's rear end.
Right.
That's how they use the term. Just on backwards.
So we just kind of honed in on, I'm going back to the 140 now, we honed in on that operation, made the yields a little better, had a lot of fun with the people. And then we decided to, Conshohocken came along. Allen Wood was one of the first casualties of the turn down in the steel industry. They had a blast furnace, so they had to make big batches of steel. We had done the right thing making electric furnaces here. And so they had a huge inventory problem. And so they were one of the first casualties, 1977. We bought the mill and restarted it a year later, 79 or so, and operated it with Al Eastburn and Vince Newhouser, Bob Shaw were all instrumental in starting that mill up. During that period of time, as that mill started running one turn a week, the 120-inch mill, which is here, started turning down. And we went through the throes of tightening the belts and the layoffs. And I'll tell the quick story that when I came, the price was here and $600 or $700 a ton, and the slide started somewhere in the late 70s, and that slide continued until about 2.5 years ago. And we got down in Conshohocken, we were selling carbon steel for $299 a ton, and all through this time, where as the sales price slipped, and there's reasons for that, and I'll cover that real quickly. As that price slipped, we did one thing after another to keep our costs coming down. We changed the yield. We changed how long it took to heat a soaking pit. We laid off supervisors. We combined jobs right on down the line. Whole departments were lost. The engineering department was probably at one point 60 or 70 people, and it's now, I think there's probably how many engineers here? One. Okay. That's an example. The industrial engineering department's gone. And I could go on, but there's been a whole tightening of the belt. And during this whole time, Lukens stayed profitable and slightly under the power curve, if you will. Now, all of a sudden, one of the sales guys said to me about a year ago, price pops back up. And suddenly you have a nice margin going. And they say, oh, that's because we got our price back up. No, that's because of all of the improvements that have happened over the years in the manufacturing departments. I believe it's why we're making a tremendous amount of money right now. That was a very difficult time to go through from 76 to within a couple of years ago, 2004 and 5. And I've worked for one company with about 6 different names through that whole thing. So anyway, the 120-inch mill started down. It eventually closed, and the 110-inch mill in Conshohocken started to pick up, went from 1 shift to 2 shifts to 3 shifts, and the 120-inch mill, which was a much older mill, was shut down. That was Rod's baby. The old 120, it was tough to shut it down, but we did. And that was part of that consolidation that went on, and we moved material to Conshohocken and rolled it down there. I went down there in 1988 and took a lot of the rolling information and experience that we'd gained up here in the 142.6 and took it down to Conshohocken. We started Conshohocken at that point in time, when it was first started. Al and Bob Shaw got it automated, and with the first Classim modeling system to control the mill with a computer and to do dynamic pass scheduling. The first one installed in the United States was installed at Conshohocken. That system is still in use today. An older brother of it is installed on the 140-inch mill today. In 1992 at Conshohocken, we installed something called slab shape rolling. And can I write on this?
Yeah.
That's a screen.
That's a screen.
Is there pens up there? Do you need help here moving that thing?
I don't know, where can I write on? I don't want.
Yeah, no, that's fine. 'Cause it,
Oh, okay. Yeah, maybe a pen, maybe not.
I think there's one right in the drawer over here. I'll get it.
All right. What we did in 1992 for about $4 million, we installed slab shape rolling, which I'm following on Rod's comments about yield. What we did, this is okay. When we were rolling a slab, we would, on the last pass, we would make that slab bow tie shape. And I'm drawing in 3D. So that when we rolled it, this would end up with a little bit of a tongue on it. The natural tendency, if you didn't have this extra edge on it, was for it to be round. And so the combination of these two shapes ended up with something that was almost perfect for using the maximum length on the plate. And that was called slab shape rolling. That uses a very high pressure hydraulic system. And there's probably 3 of those installed in the world, and one of those is at Conshohocken on the roughing mill. It improved our yield about 3% when we installed that in 1992. So that was one of the technical improvements that we had. Thanks. Jim. Get this back down. Then, and I'm going up in history, and of course I'm going to be around a while, and there's a lot of people that know this story, so I don't have to, for the camera's sake, extend this too much longer. 1991, I'm in the 110-inch mill, up in the pulpit, of course, where I always stayed, and I see down at the end of the run Bob Shaw. And I said to the operator, of course, Shaw at that point in time he may have been president of the company, I'm not sure. Anybody know? Sure, 91.
Not quite yet.
Shaw was not at Conshohocken, but he was up here in some capacity. And he was down there, and I saw him at the end of the run with a tape measure. And I said, who is that? Who's got a tape measure out on my run in the way? And they said, oh, it's Bob Shaw, I think. And I said, yeah, it is Bob. So I go down and I go over to Bob and I said, can I help you hold the tape measure? Because he's trying to feed this thing across the run to see how wide the run is. I said, what are you doing, Bob? He says, I'm measuring you up for a Steckel mill. And I said, oh my God, Bob, don't do that to me. And so that was 1991, and of course then we went ahead and did the engineering work. It took a year to decide to do it, a year once we decided to do it to decide on who was going to do it, a year to engineer it, a year to install it, another year to make it run right. So somewhere around 1996, I always joke with everybody that I'm only 30 years old. And this is what a Steckel mill could possibly do to you. I've got a real short film that I'll show. A Steckel mill, I've got a couple slides actually, and I'll go through these really quick before I show the film. This is a little bit of history. Upside down. Was a concept by Abraham Steckel, who is an American from Youngstown, Ohio, patented in 1927. And it was the first foreign Steckel mill installed and it was installed in 1951 in Sweden. But the Steckel mill that was built in Youngstown, Ohio, actually stayed in business and was shut down in 1955. This is a picture of Mr. Steckel, and this shows you a picture, a drawing of the side view of a Steckel mill. And it's a 4-high plate mill with heated coil boxes on both sides so that you can put the piece up into the coil box and keep it hot. And as Rod said, it gets cold as it gets longer. And so down at Conshohocken now, in the old days we could only roll 1/4-inch plate 600 or 700 inches long. Now we roll 1/4-inch plate 1/4 of a mile long. So the yield is extremely better. In the old days the yield might be 70 or 80%. On a piece of 1/4-inch. Today it's 95% on a piece of 1/4-inch. This is Rod's favorite magazine, Iron Age. Talked about the Steckel mill, and this was December the 31st, 1931. This wonderful new thing that's going to lower your costs and improve your productivity and your yield. And it was the best of all, and it was designed to be a poor man's strip mill. But what it's really turned into is, because it could never compete with the strip mill in quality, it's turned into a rich man's plate mill. And so all the plate mills that are being built now are having the Steckling capability attached to them if they're light gauge. This is a side view, and if you didn't know that this was a 1930 picture, you'd swear that it was Conshohocken. Well, what's the difference between this and what I have is the computer controls that are on the mill at Conshohocken is what makes the difference between this, which was largely a failure of a mill. It did not work properly. There's too much going on for a human being or any bunch of human beings to control. It actually took a computer and digital drives from the 70s and 80s to really get that monster of a mill to work properly so that you can roll a piece a quarter inch, a quarter of a mile long. It's a good concept, but you just couldn't execute it because you didn't have the technology to control it. This is a modern Steckel mill, which is what I'm going to show you a picture of, allows efficient production of wide, thin, low volume sizes where you couldn't before. When you rolled quarter-inch plate on a 140-inch mill, quality was suffered. You probably, from a yield perspective, you were a C minus. From a flatness perspective, you were a D minus. From a gauge control point, you were probably a C. And with the Steckel mill, all of that all becomes A to A minuses right along. So it really improved the rolling process. Before, the customers couldn't get thin plate, and now they can. This is a side view of the mill at Conshohocken. The plate mill, this is the 4-high plate mill in your quilling box. This looks just like what was in 1930. I think the best thing I could do now is show you the film of the Steckel mill. The Steckel mill cost $150 million paid out of pocket, but it probably cost us another $100 million in problems. So, okay, thanks, good. Let me show you this quick film. Here we go, Sam.
Mittal Steel USA is headquartered in Chicago, Illinois, and is the largest steel producer in North America. Our steel products include hot-rolled, cold-rolled, and coated sheets, tin mill products, wire, rod, bar, semi-finished shapes and rail products, and carbon and alloy plates. We produce plate products at our mills in Burns Harbor, Indiana, and Coatesville and Conshohocken, Pennsylvania. Additional slabs and ingots are provided by Mittal facilities in Cleveland, Ohio, Indiana Harbor, Indiana, Steelton, Pennsylvania, and Sparrows Point, Maryland. Here's a look at our Eastern Pennsylvania plate facilities in Coatesville and Conshohocken. Mittal's Coatesville and Conshohocken plate facilities have a specialty focus. Other companies offer many forms of steel, but we specialize in plate. We are the plate professionals. We are customer-driven. Our people have only one goal: to satisfy the customer. That means producing the highest quality plate steel and shipping to the customer on time. To do this, we continue to invest in our company. We have dramatically improved our production facilities, including our electric melt shop, our rolling mills, and our heat treating complexes. Our plate facilities are world-class, and we aim to keep them that way. Our modernized Coatesville electric melt shop allows us to improve internal quality. Automated rolling mills, including the Conshohocken Steckel mill, allow us to make plates to closer tolerances than ever before. And our heat treating facilities produce specialized steel to exact specifications. We continually upgrade our environmental controls to protect air and water quality in and around our plants. Our technological growth gives us a strong competitive advantage, and our future plans are even more ambitious. we've developed our plate-making capabilities over nearly 2 centuries. In 1825, we made plate for the nation's first iron-hulled ship, and today's Navy continues to rely on our plate for its submarines and aircraft carriers. Our products are being used to rebuild America's infrastructure, to build construction equipment and refinery and chemical process vessels, and for other applications that demand the highest quality plate steel. We're proud of our heritage, but we're not content. We strive to get better every day. That's the kind of company we are. We make a wide range of high-quality carbon, alloy, and clad steel plate. Here's a look at some of those products and the technologies that make them possible. Many of our thin plate products are rolled at our Conshohocken plant. Conshahocken's roughing mill reduces slab thickness from 9 inches to between 1 and 3 inches. The mill is fully automated and equipped with automatic gauge control. From the rougher, the steel enters the 110-inch wide Steckel mill. This state-of-the-art mill can process carbon, alloy, and stainless steel as coil or discrete plate. The Steckel mill has coil furnaces on either side, which wind and unwind the hot strip of steel as it passes back and forth through the rolling mill. The system reduces radiant heat loss so the steel can be rolled longer and thinner. Advanced computer systems control thickness, width, shape, and surface quality. Automatic work roll bending virtually eliminates plate crown, and automatic gauge control ensures precise dimensional accuracy. The mill rolls steel coils to thicknesses between 0.118 and 0.625 inches, up to 102 inches wide, and as long as a quarter mile. Online controlled cooling allows yield strengths up to 80,000 pounds per square inch in certain product grades. After cooling, the steel is wound on a downcoiler capable of producing coils weighing as much as 40 tons.
Any questions about the film? With that,
That's what the education is. For somebody who's been through the 3-high mill, the 206-inch mill, and then you go down and spend time with Mike at Conshohocken. Have a nice lunch and a drink, but have a nice time in the mill. It's the education. It really is an enjoyable trip.
with that, I'll ask if there's any questions, I guess, from the group. Scott?
I have a quick question is, what, I guess crowning is a problem and the straighteners, but what is the tolerance? I mean, flatness, trying to get a true flat plate, but I'm sure there's some sort of tolerance on that.
I'll give you the flatness. The flatness of a plate is you're talking about controlling to some extent the ratio of the thickness to the difference in edge gauge to center gauge. We call that crown. Okay? So if a plate is 1/4 of an inch thick on the edges, 0.25, and in the middle it's 0.28. So it's 3/100ths or point, let's say 0.253, 3/1000ths crown, okay, at 1/4 of an inch. You must maintain that 3/1000ths crown to thickness ratio all the way up through the pass schedule, or all the way down, if you will. So if you know you're going to have 3/1000ths at the end, when you start rolling, let's say at 1 inch, you've got to have 4/1000ths, 4 times that amount, 4 times 1/4 of an inch, 1 inch. So you need to have 12/1000ths crown at 1 inch, so that when you get down to 1/4 of an inch, you're going to have 3/1000ths. You're going to, well, how do you know that? Well, that's all done with modeling today. We know, given the temperature of the steel, the grade that we're rolling, the capabilities of the mill stand, we make a plan ahead of time. Given the actual performance of that particular piece in the rougher, we instantly run it through the computers, and it says, here's our plan. We're going to make this a 1 inch transfer bar with 12/1000ths crown in it, and we're going to take these 4 or 5 reductions, and when we get down to 1/4 inch, we're going to have 3/1000ths of an inch crown. And we control that plan by using roll bending to get exactly the crown that we want on every pass, given the thickness of the plate that you're actually producing. That computer algorithm of actually knowing what you're rolling and adjusting to it is done 40 times a second with the computers, using hydraulic actuation of your work roll bending and changing of your thickness with your hydraulic gauge control system. So there's some heavy-duty computers and heavy-duty hydraulics operating to allow you to do what was a good idea in 1931. You just couldn't pull it off. Today, with all the computers, you can make a plan and execute that plan. And that's why I'm only 30 years old.
Are you saying it's getting easier then?
It is easier. For the human beings, it's easier. Before, it was a mess. Today, it's much easier. The trick is for us to stay out of trouble, and that's what the human beings are good at understanding, is we sit and watch and supervise the operation and know when we're getting in trouble and when the machine isn't working correctly. And because we're experienced at solving problems, we're good at doing that. What we're not good at doing is operating 40 times a second, making changes.
I have another question is, you have an ingot or a slab, and as you said, there may be different temperatures of the slab in different phases. Like if you have a big ingot, it's probably a little bit warmer in the middle still. How would you, or was it necessary to maintain a constant temperature of the slab or the ingot as you rolled it?
Well, in a Steckel mill, that's probably the worst of all problems. It's because when you go up on the drums, the ends of the plate, as it comes out of the mill, stops. And that end of the plate doesn't go up on that drum. And so it stops in the mill for about 4 seconds. And then it reverses and it goes back and gets on the drum on the other side. And then the other end comes through. So we actually have a head that's cold and a body that goes through the mill very fast that's probably 300 degrees hotter than the heads and the tails are. And then in the middle of that, you've got a transition where the temperature goes from relatively cold to body temperature warm or hotter. Well, how do you deal with that? Well, in the Steckel mill, we don't roll one plate. Every pass we roll 5 plates. We roll a head, a transition, a body, a transition, and a tail on every pass. And we set up every pass with that plan so that when we get to the final thickness, we end up making the same thickness, the same crown, and the same forces, at the same forces in the rolling mill. And we do that by making different gauges, different crowns, different thicknesses, all the way through the rolling schedule. So you're rolling, if you rolled 5 passes, you actually rolled 5 times 5, 25 passes, because every piece is treated differently in the Steckel mill. It's one of the problems Chris has in the rolling mill in the 140, but not nearly as bad because it's somewhat thicker, and so the temperature differentials are less. But that's what gauge control does for you, is a quick lesson on gauge control is that as you go through the rolling mill, the rolls want to be spread apart by force. If you know the thickness between those 2 rolls, you know the thickness of the plate. It's that simple. There's no magic spring back or any of that. So as the plate goes through, well, the question is, what is the opening in the mill? Well, you know what you started with, but you don't know how much that big housing sprung. But we can figure that out engineering-wise. There's a known amount of spring in every housing for a separating force. And so that is done in the computer 40 times a second. Says, what is my force? How much is that housing stretching? And therefore, what is the thickness of the plate? And it says, oh, okay, now you're making the wrong thickness. Well, 40 times a second, we feed hydraulically back to a gauge control hydraulic cylinder that moves the mill up and down so that we actually make the right gauge. Well, how do you know what gauge you're making? We x-ray the plate as it leaves the mill. And so we feed back through that x-ray gauge to the actual hydraulics, to the model, what actually is occurring in the mill stand. So it's you almost have to come see it with me.
I love it.
It's a long way from pushing the pedal, I'll tell you. A long way. over the years, you can see the difference. And that's what does most interesting to me is to take a visit to Conshohocken today, Scott, and see what the modern technology is, and remembering how we made plates in Coatesville years ago. There's a hell of a difference, I can tell you that.
Right, you still run the
You
2.6.
can start at the 2.6 mil on a Wednesday and see how it was done back then. There's no computers down there. You still got the foot pedals. We stopped using salt. It's on a low salt diet now because they say the housing's rusted away too much. But we do throw the bags and, you know, evolve to the 140 and go see the speckle mill, and you can see the whole evolution of plate production.
Other questions?
You kind of alluded to it. You do know what you're making when you're rolling it? I mean, you know that this is an aircraft carrier part, or?
Oh, absolutely.
You know, because the quality of the steel and the order, maybe?
Right. You've probably, well, there's, for example, in the X-ray gauge, you know the actual chemistry of the piece that you're rolling, right down to the finite molecules of what you're rolling. And so you know when you X-ray through that plate how much you should get out the other side for it being that. Now if it's a different chemistry, you know that you're going to get less or more radiation back through the X-ray back through that. And yes, you know exactly, and you know the customer, you know the grade, everything about that plate, you know.
Was that always true? Did you in the old days?
Yeah.
You knew?
Yeah, you knew, but you just couldn't account for it. The screwman in the old days would go, oh man, what a day. He'd look through his charge papers and he'd go, oh, this is going to be a mess. You know, this is going to be a day.
It's going to be a tough day or a good day.
It's really fascinating. I mean,
Yeah,
I've
it
never
really is.
been in a rolling mill, but
I can just
absolutely.
see it.
Well, you saw some there in the film.
Yeah,
Yeah.
we thank you for sharing
Yes,
this with
it's
us. We
fascinating.
learned a lot.
I
Yep.
remember when the charge papers used to be a different color for
I
our
think they
degree.
still are.
We still are, yeah. We're yellow for stainless, green for carbon. That's.
Rod, you say it's a green day today. Right now, Conshohocken's making all armor plate, all the stuff being made for the Strikers, the Humvees, stuff going to Iraq, the M1 tanks. It's all being made at Conshohocken and Coatesville. There's a couple other mills on the sidebar, but we are flat out making armor. We've had a couple guys at Conshohocken, for example, that had kids in Iraq that were hit by, vehicles were hit, and the guys' lives were saved with the armor plate that their dad had loaded on a truck. So, small world.
Can we get one of those used trucks?
When I visited Conshohocken, I got a piece of that armor that he's talking about, and he has in the shearing operation. I picked up a scrap end and put it in my pocket. My son has that piece on his desk today in Afghanistan.
Does it have to be thick to be safe?
No, not
No,
necessarily.
I was just wondering if it's.
The armor plate is a special type of steel that has different chemical elements than carbon steel would. Unfortunately, when a piece of steel gets hit by a projectile, if it's carbon steel, the back of it spalls off. And what was one bullet coming through comes out as 10 bullets in the back, little pieces.
Oh my God.
Armor plate, the bullet hits, the back of the plate may deform, but no pieces come off of it. Now, if you have a huge projectile, it will rupture the thinner plate. And so therefore, your tanks are made of 2 and 3 inch material. Your lightweight vehicles that the troops are in, because they have to be lightweight, are a thinner type material. But we're making composite armor where you have armor and ceramics and armor together and doing all kinds of things. And it's, you know, it's like radar detectors. You know, they make a better radar on the police and then we get a better radar detector. And, you know, it's one-upmanship. So.
Well,
Right.
no other questions. Really, again, you know, thank you very much for coming tonight. I think it's about 50 years of history here this evening, and you know, Lukens and you know, ArcelorMittal, it continues to roll today, and we're very proud of everything that you all do for us. And you know, we again just thank you very much for being here and sharing your stories with us. So thank you very much.